Okay. Hi guys. So I want to explain how to do Lab 109 to you. So I want to give you some help for Lab 109. 109. So the idea for Lab 109 is this. Suppose you have two objects. One object is called M1, and then there's another object, we'll call it M2. And let's say that this object is moving this way, and this object is moving that way. So this one is going at a certain speed. Let's call that speed v1. This one is going at a certain speed v2. Let's put a number here. Let's say this is 1 meter per second. Well, this one is moving the other way, so whatever speed the other one has, it has to have a minus sign. So let's say this is going at minus 2 meters per second. Okay? And let's say that this object weighs 1 kilogram and that this object M2, let's say this one weighs 2 kilograms. Okay? All right, so this is basically the setup to talk about what's called conservation of momentum. Okay? We can also talk about conservation of something called energy. But this is what the situation you want to be thinking about. Momentum and what's called kinetic energy. So basically, if you think about this situation, what's going to happen is that these two objects are going to hit each other. And then after they hit each other, various things can happen. One thing that might happen is that they might bounce off each other so that after they collide, um, this is M1. M1 will be going the opposite way because it hit M2 and it bounced off. And likewise, M2, this one might be going the other way because it hit M1 and it bounced back. So these are just some possible things that could happen. Now, another thing that's possible is that because this one is much heavier than that one and it's going much faster, after the collision, they could both actually be going in this direction. So there's many things that can happen. And the way you figure out what happens is you do something called momentum, which means you do a calculation and it will tell you which way things are going to go. So the idea is you calculate momentum. Momentum is denoted by P. P is momentum. So for the picture I drew before, over here, the momentum of the system P is equal M1 times V1 plus M2 times V2. So that would be equal to M1 is 1 kilogram times V1, which is 1 meter per second, plus M2, which is 2 kilograms, times V2, which is equal to minus 2 meters per second. The thing with momentum is it's important to remember that because M2 is going this way means negative. This is the negative, so you need to put a negative sign there. So then if you calculate the momentum, you can actually add up these numbers, you get the momentum equal to 1 times 1, which is 1, plus 2 times minus 2, which is minus 4. Okay. So then if you add everything up, you get a total momentum of 1 plus minus 4, minus 3 kilogram times meters. So that's what's called the system momentum. And the important thing to understand is that this momentum is going to be conserved. So what that means is that after the two objects hit each other and bounce off, whatever happens, this number is going to be a constant. So after they hit each other, the momentum is going to be equal to P, we'll call it final. It's going to be M1 times V1 final plus M2 times V2 final, where now velocities of the two objects are going to change. Okay. These velocities are going to change. So remember, after the collision, that's over down here, after the collision, M1 is going in the opposite direction it was going before. Initially, M1 was going to the right, this way. But after it hits M2, it's going to go backwards. And then for the other one, M2, it also is going to have a different velocity because it's going to hit the object and it might bounce off. But this rule of conservation of momentum says that this must be equal to the initial momentum equal to minus 3. So it basically gives you a condition constraining what's going to happen. So what you're going to do is you're going to go to the experiment and you're going to test this. So let's set up the problem the way I set it up, and we'll see if we'll try to do this. We're going to set M1 equal to 1 kilogram, M2 is 2 kilograms, V1 is 1 meter per second, V2 is minus 2 meters per second. So we go over to the experiment and we're going to do elastic. So first we'll choose elastic, 100% elastic. I'll tell you what that means later. And you're going to click on this button, more data, so you can choose all the masses. So we're going to have M1 is going to be 1, and M2 is going to be 2 kilograms. Remember, that's what I said. And the position is M1 is here, and M2 is here. The position is what the lab instructions call L1, L2. This doesn't really matter. Just leave them the same. You can say L1 is 1, L2 is 2. And then the important thing is that the velocity of this one is going to be 1, but this one should be minus 2.0 meters per second. Okay. So now what you're going to do is you set it up. So you're going to hit play. And, well, I'm going to reset that actually. I'm going to hit play, and now I'm going to hit pause. And you can see what happened is now this is after the collision. I'm going to reset it one more time. So first they go together, then they stop. This one actually stopped, and this one went the other way, right? So that means that the final velocity, V2F, is 0, and the initial velocity, the final velocity of number 1 is minus 3. So the idea is now you go back and look over here and say, okay, now I can start doing something interesting. I can start basically figuring out what the final momentum is. What that means is, look at this equation. This is the final momentum equation. We said m1 times v1f plus m2 times v2f, that should be equal to the initial momentum, which is minus 3. So if we go back and look at the result of our experiment, it says that After the balls hit each other in the final situation, ball 1 has a velocity -3 and ball 2 has a velocity 0. So let's plug those numbers into the momentum formula, and we get that the final momentum, P final, is going to be M1 times V1, just rewriting the equation, plus M2 times V2 final. But the masses don't change, so it's just 1 times V1 final, which is -3. Where I got the -3 is I looked at the data from the experiment, and it says that the velocity after they hit each other, final means after the collision, is -3 for the red ball number 1. This plus M2, which is 2 times 0, if you calculate this, you get 2 times 0 is 0, 1 times -3 is -3, and what you see is that the momentum is conserved. So the final momentum is equal to -3, which is equal to the initial momentum. And that's called conservation of momentum, okay? Equals -3. So we already saw that the initial momentum was -3. We calculated because we assumed that the initial mass is 1 kilogram moving 1 meter per second. The object 2 has a mass m2 of 2 kilograms. The initial speed -2 meters per second, and we calculated this. And then we saw in the experiment that after the two objects hit each other, this one didn't actually bounce back, but it stopped. Generally speaking, after the collision, you don't know which way it's going to go, but what you do know is that the momentum is always going to be conserved, which means that it's always true that initial momentum is equal to the final momentum. And that's what we want to test in this lab. So the idea for the experiment is that you're going to go back here and you're going to change, you're going to restart, and you're going to put your data into the workbook. Here's the workbook. So if you look at the workbook, the way you would enter the data is you would put mass 1 is 1 kilogram, mass 2 is 2 kilograms. Initial velocity was 1 here for mass 1, initial velocity was -2 here for mass 2. The initial momentum, you can use Excel formula, it's going to be equal to this times this plus this times this. You get -3. And then oh, sorry, I made a mistake. This times this. The initial momentum of just that object is 1, and then the initial momentum of that object is that, and then you add them together. Each object has a momentum, and then the total is equal to this plus this, so that's -3. And then we saw the final velocity was -3 for this one and 0 for this one, so that the final momentum is going to be equal to the mass of velocity here. And then all same thing for this one, it's equal to m2 times the final velocity, which was 0. And let's see. Looks like there's a little bit of a mistake in this chart. This should not be here. It should really be here. So you can correct that yourself. You can move that over. So that should really be over there. Sorry about that. Because those are just telling you not to calculate the combined velocity. So let's move those over. Move all of those over 1. So the final momentum here is the sum of the two objects' momentum. M1 V1 plus M2 V2. And you see it's -3. Okay. So then how you do the experiment is you put the data and then you get initial momentum here and you basically total for the system you want. -3 equals -3. That's just what we did before. And this is the data that you want to remember. And then what you do now is you go back here and you change things. So you could make the initial velocity 3, just make one small change and then redo it. See what happens. Now you see you get totally different answers, right? So now instead of having initial velocity of 1 here, I changed it to 3. I do the experiment and now you see this one's going that way and this one's going that way. So now what you would do is go back to your data table and you would enter for the new experiment. I didn't change the masses. M1 is still 1, M2 is still 2. But I did change the initial setup. Here now, this one has a velocity of 3, and this one has the same velocity, -2. So I just changed one thing, but it completely changed the result of the experiment. So if you look back, start, M1 has an initial velocity of 3, M2 has an initial velocity of -2. I do the experiment, I pause it, and now, wait, let me, one more time. Now you read this number. This is V1 final. You copy that, you go to Excel, and you're going to put that here, and then you go back to your experiment, and you copy V2 final, and then you put that here, and now you use the same formulas to calculate the momentum, okay? So here the momentum is going to be equal to this times this plus this times. See, the total momentum is -1. And if you calculate the total momentum after the collision, that goes here, final momentum for the system, you should see that it's also equal to M1 times V1 final, 3 plus 6, 7, plus M2 times final velocity. And if you do the calculation, you see it's -1.01. -1 is basically the same. So the idea for this lab is to basically keep calculating the final momenta and just write down these are the numbers. And basically what you see is that they're going to be the same. So you should eventually get a plot where it's just a straight line and it's just, you know, a slope of 1 because it's the same. Initial momentum equals final momentum. However, for part 2, you repeat everything the same. The only thing that you change is you go to this elastic and you go all the way to 0. Now when you do that, it's going to change. Now they're going to stick together. And what you'll see is that if you put in the final initial velocities, final velocities, all the calculations are the same for the inelastic collisions. You do everything exact same. But you will see that the momentum is still conserved. Again, you're going to have to move this over because it's not in the right place. Control X, Control V. But you calculate, all your calculations are exactly the same. But you will see the momentum is conserved. However, what you will also see is that if you calculate something else, and by the way, inelastic means that two objects stick together after they collide. That's what that means. When that happens, the momentum is still conserved. So the momentum before a collision equals momentum after collision. That's always true. So you will see PI equals PF. Always, momentum is always conserved. Always conserved means it always stays the same. Now, the last part of this lab is that you also want to calculate something else. You want to calculate something called kinetic energy, KE. And the way you do that is KE is very similar to momentum, except it has one small difference. Instead of m times v, it's 1/2 times m times v squared plus 1/2. You add up all these um, terms, 1/2 m2 times v2 squared. That's the initial kinetic energy. So for our example, initially, m1 is 1 kilogram and its speed is 1 meter per second. So the kinetic energy then is going to be 1/2 times 1 times 1 squared plus, over here, initially, before the collision, m2 is 2 kilograms, then speed is -2. So it's going to be plus, that's a plus, not a multiply, plus, let me erase that, it should be plus 1/2 m2, which is 2 kilograms, times v2, which is -2 meters per second squared. Becomes 1/2 times 1, that's 0.5 plus 1/2 plus 4 is going to be 4.5 joules, which is the unit for energy. So what you will see is that the kinetic energy is conserved, which means the kinetic energy is conserved after the collision when it's elastic. So if you go back and set this to look at the elastic case, and you set the initial velocity to 1, like our first one, what we got was that the final velocity was -3 for object 1 and the final velocity was 0 for object 2. So now if you go back and compute the final kinetic energy, what you get is let's calculate the final kinetic energy, KE final. That's going to be 1/2 times 1/2 times 1 kilogram times 3 meters per second squared plus 1/2 times 2 kilograms times 0 meters per second squared. And this is actually equal to 4.5 joules. So you see the kinetic energy is constant, energy is conserved for elastic collisions. So for elastic collisions, the final kinetic energy is equal to the initial kinetic energy. And the way you're going to put that into your data is you're going to, let's say you go to elastic collision, you go here, the initial kinetic energy here, it's going to be equal to just that formula. It's going to be 1/2 or 0.5 times m1 times v1 squared, I'm just going to multiply again to square it, plus 1/2 times m2 times v2 squared. You have to square v2, so you multiply by it again. Okay, and if you do that, you should see 4.5, right? And it does turn out to be 4.5. Now let's now calculate the final kinetic energy. That's going to be equal to 0.5 times m1 times v1 final, the final velocity of m1 squared. Let's square that. Whoops. Plus, I have to add the 1/2, 0.5 times m2 times v2 final squared, 0, but even though it's 0, I'll include it anyway. See, so you see the initial kinetic energy is the final kinetic energy. So you just use that formula and you'll see the initial kinetic energy equals the final kinetic energy. The initial momentum equals the final. Each time you go back and you change something, you change one of the initial speeds. You're going to repeat the experiment 10 times. Each time you do a new experiment, you're going to change either the initial speed of m2 or the initial speed of m1, just change it a little bit. Or you can change the masses. Change the mass from 1 kilogram to 5 kilograms. See what happens. So that's the idea. Now, when you get to inelastic collisions, everything works the same way. But what you'll see is that when you calculate the initial momentum and final momentum, you use all the same formulas, and the initial momentum is going to be equal to the final momentum. So for the inelastic, you have to remember to change this dial down to 0 when you do that, when you start doing this. That's 10 different experiments. But what you'll see is that the initial kinetic energy is not going to be equal to the final kinetic energy. And that's because in inelastic collisions, energy is not conserved. However, the momentum will always be equal. This number, the total momentum initially, will be equal to the total momentum after the collision. Final kinetic energy and initial kinetic energies, these two, those are not going to be the same for the inelastic. So there's two sheets, Excel sheets, and you have to go to both. Now, when you plot your final plot, all you need to do is plot these numbers versus these numbers, and then these numbers versus these numbers. Sorry. You plot the initial momentum data versus the final momentum, and then you plot the initial kinetic energy versus the final. So basically, you're going to take some columns. Initial momentum total for the system, and then final momentum total. So you're just basically going to copy the numbers here to here, and the number here to here, etc. All these numbers, and then you're going to take the final momentums, this number here, here, and this number, and put them. And then you're going to create a plot. And you do something similar for the kinetic energies. Then you go to the, you do this for both data sheets. So it's kind of a lot of work, okay? But that's pretty much it. And when you do the plot, you know, you can try to add a best fit line, but that's not so important. I just need to see the plot. You don't need to worry about labeling the plot. Okay, so that's pretty much it in a nutshell. Please let me know if you have any questions. Remember, kinetic energy is 1/2 the mass times the speed squared for all, and you add it for both objects. And then the momentum is just the m1 v1 plus m2 v2. But that's the initial momentum, and then after they collide, the velocities change, and the momentum is going to be m1 v1 final plus m2 v2 final. But this should actually be equal to the initial momentum. So this number equals this number, even though the velocities change. All right, let me know if you have any questions. Thank you.